Alright, our very last chapter. Woohoo! Chapter 10. Chapter 10 is on something called correlation. And it's a pretty short little chapter because we only do like the first couple sections in it. And a lot of people really like this chapter because it's much more algebra based. It's talking about lines and linear equations, y equals mx plus b. Okay, we're talking about correlation. Correlation exists between two variables when the values of one are somehow associated with the values of the other. We can often see this relationship between two variables by constructing a scatter plot. We talked about scatter plots way back in chapter 2. I'll tell you now how to do them on your calculator. So remember, with a scatter plot, you're plotting the points, but you don't actually try to connect them in any kind of line. If the scatter plot is basically going uphill, remember you always read left to right in math. So if I'm reading left to right, which would be this way, this scatter plot looks like it's going uphill. So that gives it a positive correlation. So again, if I read left to right, this scatter plot looks like it's going downhill. That gives it a negative correlation. Those R's down there I'll talk about in a few minutes, but they support that positive correlation, negative correlation. See how the first R is positive? That indicates uphill. See how the second R is negative? That indicates downhill. We can also have no correlation, which basically looks like that shotgun blast. It can also be no correlation if it obviously curves. And like a lot of times you won't have the whole thing like this one, you'll have like that much that I just drew. If you can tell from the scatter plot that it's obviously curving over, then it's not a linear correlation. It's a correlation. That might be a quadratic correlation. And that's the other part of 10 that we don't do. But we're only doing linear correlation, so unless it looks like it's going in a line, we just consider it having no correlation. So linear correlation coefficient, and you need to know that name with this symbol. So R is the linear correlation coefficient. It's a numerical measure of the strength and direction of the relationship between the two variables. And like I said, there's other correlations besides linear, but we're not going to. Some properties of R. R is somewhere between -1 and +1. If we change the values of either variables by converting their scale, the value of R doesn't change. So for example, if I measured things in inches and then changed my measurement from inches to centimeters, my graph would move around, but it wouldn't change shape at all, so my R would stay the same. It also says the value of R is not affected by the choice of X and Y, that I could interchange them and it would stay the same. So X is your independent variable, Y is your dependent variable, so whatever your X is, you're looking at that and going, does it make the Y go up or down? This is saying I could swap that and I would still get the same shape graph, so R wouldn't change. In this book, in real life, you'd have to decide which one was X and which one was Y based on what you want to know. Do you want to know if gas consumption goes up because gas prices go up, or the other way around? Do you want to know if gas prices go up because gas consumption goes up? So in real life, you have to decide which one you want to be the independent, which one you want to be the dependent. In this book, and in the test, and in the notes, and etc., whatever it gives you first in the table is X, whatever it gives you second is Y. So they just make it easy. R is the strength of the linear relationship. We've already said that. And R is very sensitive to outliers. So if there's any outliers, that's another reason you want to look at the scatter plot first. it can really mess your R up because it's trying to consider all the data values. Okay, so some more specific properties of R. Like I said, R has to be between -1 and 1. If it, however, let me say it again. The closer it is to -1 or 1, the stronger the linear correlation. Okay? If R equals 1, it's a positive linear correlation, and it's a perfect positive linear correlation. So it's a line going straight up. If R is -1, it's a line going down. So 1 and -1 is a perfect line. Anything close to 1 or -1 indicates a strong correlation. A positive R indicates a positive correlation, a negative R indicates a negative correlation. Values of R close to 0 represent a weak linear correlation. 0 itself means there's absolutely no linear correlation. Okay, so in order for something to be a linear correlation coefficient, the sample of paired data values, x and y, have to be from a simple random sample of quantitative data. We can only do scatter plots of numbers, not labels. You look at the scatter plot, see if you think it's going in a straight line. You look for things like that curving or outliers. If you have outliers, consider the effect of those when you're calculating R. But to truly decide if it's a linear correlation, we're going to find the R on the calculator, and we have to compare it to an R on table A6, which I will give you in class. There's also one in D2L under Chapter 10 that you can pull up. The table A6 is all the determined values that R has to be at least to be considered linear. Okay? So if it's on table A6, your R has to be that or bigger, or it's not linear. So you can't do this without that table. And that's what that last part down there means. If the R you get in your calculator, and it's got absolute values around it, because I don't care if it's positive or negative, I'm just interested in the value that it is. If that R is bigger than the R critical, which is the one we get off the table, then we consider this linear. So this is a little piece of that table. On the table, you have your N. Your N is your number of data pairs. You have an alpha of 0.05 and an alpha of 0.01. We're only going to use the 0.05. So if I had 6 data values and I'm using 0.05, my R critical would be that 0.811. So any R I get in the calculator would have to be bigger than 0.811 for me to consider this a linear correlation. If it is linear, then I can get a line of best fit. This is the same line as in algebra, y equals mx plus b, but for whatever reason, in this book in statistics, we have to use y equals a plus bx. Same thing, just different letters and in reverse. In the calculator, it's the second len reg that we go to, and I'll show you that in just a second. Once I have this equation, I can use it to predict new values of y. If my data is not linear, you have to do the average of the y's as your prediction. So don't use a linear equation to make a prediction of something that is not linear. Another thing we're going to get in the calculator is R squared, and again you need to remember that coefficient of determination has the symbol R squared. It is the proportion of the variation in y that is explained by the linear relationship between x and y. So the coefficient of determination determines the amount of variation in y that is due to the line of best fit. And we'll do an example with that for that to make more sense. Okay, so here's your example. This is out of the book, and it was the cost of a slice of pizza and subway fare. And I believe this was in New York City. And weirdly enough, this has an almost perfect correlation. So somebody noticed that whenever the cost of a slice of pizza went up, subway fare went up, or vice versa, and started recording those prices. So after several years of recording the prices, they put them together to do a correlation. So first we're going to make a scatter plot. That's always your first step. Okay? And this is what I was talking about, that you don't have to really think about which one's which. You can just always assume whatever the first one is X, whatever the second one is Y. X's always go in L1, Y's always go in L2. 2. That's not a 2. Make it a little smaller so I can put a 2 in there. 2. Nope. It's too far over. I can't do a 2. There. Always more than one way. Alright. So, put cost of pizza in L1, subway fares in L2 in your calculator. So, stat edit. So in L1, 0.15, 0.35, 1, 1.25, 1.75, 2, and in L2 the subway fares, which are almost the same. Okay, so now we're going to do a scatter plot. To do a scatter plot, you do second y equals, press enter. You make sure that on is highlighted, so have it on, press enter. Then go down to type and press enter on the first one for the scatter plot. And then it'll pop up X list, which should say L1, Y list, which should say L2. Mark doesn't matter at all. So once you've got all this set, go to zoom and scroll down and find zoom stat. Press enter. And you should get a scatter plot that looks like that over there. And see, these are going uphill in a pretty nice little line. So not only is this linear, I would say that this is a strong positive. So sometimes it won't let you get by with just linear. If it wanted to know, I would call this a strong positive linear correlation. Because it's not all spread out and positive because it's going uphill. Alright, so now we're going to find the linear correlation coefficient. Okay, this first, whoops, I'm sorry. I meant to be on a highlighter. It'd also help if I made that a little smaller. Okay, this first step, all this stuff, you only have to do once, okay? So you only have to do that again if you reset the memory or you have changed batteries in the calculator. But that you should only have to do one time. That's to make these two lines show up. So if you do this without doing that step, you'll get the A and the B, but you won't get the R squared and the R. So in the calculator, do second 0. This is the catalog. This is every single solitary thing this calculator will do. Scroll down until you find diagnostic on. Then press enter for diagnostic on. Then press enter again and it'll say done. Okay? And like I said, you'll only have to do that one time unless you reset your memory or change batteries. So then go to stat and over to calc. And if you go down, you'll see number 4 says linreg, but it's not in the right order. It says AX plus B. So keep going down. Mine's number 8. where it says linreg a plus bx. I have no earthly idea why we can't use the first one. This book uses the second one, so you have to make sure and go down to the one that says a plus bx. Press enter twice, and you should get that yellow box over there and all those numbers. Just for consistency, we're going to round to 3 decimal places. Okay? So just so we all get the same answers, we're going to round to 3 decimal places. Alright, so is this a linear correlation? Well, we do that by comparing it to the table. So first I need to know what n is. So if I count my data values, I have 1, 2, 3, 4, 5, 6 different pairs of data. So my n is 6. I'm always using 0.05. So that's at 0.811. So my R critical is 0.811. My R, which I got from the calculator, is 0.998. 0.998 is bigger than 0.811, so yes, it's linear. As long as R is greater than R critical, then we have a linear function, which we knew from the scatter plot. Alright, since it's linear, I can make a linear equation. Remember, your equation is a plus bx. So I'll look over here and get my a, plug it in for a, look over here and get my b, plug it in for b, leave the x and y alone, because they can be any x and y. And that is my linear equation. So this is your line of best fit. I can use it to make predictions by replacing the x with whatever it says x is. It said the cost of pizza is $2.50, so I plug that in there, put that in the calculator, and I get $2.40. So we predict that Subway fare will be $2.40 when the cost of pizza is $2.50. And if we were to graph that line with our scatter plot, you can see that it fits well. To do with that line of best fit, see how close it is why that R squared is high. There's very little variation that isn't on that line of best fit, so that makes the not R squared. The other thing was that coefficient determination. Now I'll explain that a little better. So from our linreg, R squared is 0.967. What that means is we can conclude that 97.6% of the variation in the cost of Subway fares can be explained by the linear relationship between the cost of pizza and Subway fares. So there wasn't much else that had to do with it in this survey, okay? There was only 2% of the variation in costs of Subway fare that cannot be explained by the cost of pizzas. And like I said earlier, a lot. So if it asks you to interpret R squared, it'd be a sentence something like this. You'll have an example like that in a little bit. Alright, so this isn't in your notes, but it's just stuff you should know, especially this very top one. Especially this last part of that very top one. And actually, I'm going to add some words over that. You'll often hear me say that correlation does not imply causation, which the whole sentence says that. But and the deal with this, well, just like the pizza thing, do you really think that every time the Subway wants to raise prices, they call the pizza people and go, hey, are you raising prices? Because we can't raise prices until you raise prices. Why? No, that's just silly. So even though there's a really strong correlation between the two, I can't say that the cause of increase in Subway fare is pizza prices. there's probably something else that drives those, like minimum wage going up or inflation. There's something else actually causing it, and I'd have to do a whole lot more research to try to figure that out. A good example of that is smoking and lung cancer. Once upon a time, somebody noticed a strong correlation between people who smoked and people who got lung cancer. But they didn't immediately go off to the presses and say, hey, smoking causes lung cancer. They had to do a whole bunch more studies and research before it was finally decided that yes, smoking is a cause of lung cancer, and thus the Surgeon General's warning on packs of cigarettes, etc. So, you can have like the pizza and Subway fares, you can have an almost perfect correlation. Doesn't mean one causes the other one. Then the other two are not so important, but worth mentioning. You don't do correlations of averages because it can mess up that correlation. And there can be a relationship between X and Y, even if it's not linear. Like I said, the rest of Chapter 10 is on nonlinear correlations. Okay, so now there's 2 practice problems in your notes. Hit pause on the video and try those, and then come back when you want to see the answer. The first practice problem in your note has to do with butterflies. It says the wingspans in millimeters and the lifespan of the adult state in days were measured for 10 species of butterflies. The results are below. First, we're going to make a scatter plot. Like I said, you can just always do it in the order it gives it to you. So we can assume that X is wingspan and Y is lifespan. Put wingspan in L1 and lifespan in L2. You probably won't need to do this first part because you just did one. So this part you don't really have to do every time, unless you've done something else with your calculator. That'll already be set up normally. It's only this one that you'll have to do every time to get that scatter plot. So if you do, you've got that stuff in your you changed your list, you put that in, do zoom stat, and you get that picture over there. Now, that ain't much of a correlation. If it has a correlation at all, I would call it a weak negative linear correlation. Okay? Weak because it's so spread out. Negative because more or less it's going downhill. So let's find R. Stat, calc, second lin reg, enter twice. And we see that R equals negative 0.644. So the negative supports that it's going downhill. And we have an R of 0.644. I don't know if that's good enough to be linear, so I'm going to go to the table. On table A6, I have 10 data values, so n equals 10. Always do alpha equals 0.05. When you look at that, you should find an R critical of 0.63. Well, the absolute value of the R I got on the calculator is bigger than the one on the table, just barely, but it is bigger. So yes, we're going to call it linear. So it is a linear relationship, but it is very weak. It just barely was bigger than the R on the table, so I can call it linear. Since I can call it linear, I can do the R squared. The R squared is 0.415. So 41.5% of the variation in the lifespan of the butterfly can be explained by the wingspan. 58.5% of the variation in the lifespan of the butterfly cannot be explained by the wingspan. And it makes sense that those numbers are like that because it's so spread apart that there would be less data values close to that line of best fit and more far away. Since it is linear, I can make an equation. So y equals a plus bx. Per my calculator, a is 61.697. B is negative 1.218 or 19. So instead of the plus, I just put the minus. You could put plus, negative, doesn't matter. Then I can use that equation. So my line of best fit is this. Then I can use that equation to make the prediction. If the wingspan is 25.7, I predict that the butterfly will live 30.4 days. Okay, the second example had to do with earthquakes. Is the magnitude of an earthquake related to the depth below the surface at which the earthquake occurs? That's a reasonable question. So they got some data. They let X be the magnitude of the quake on the Richter scale and Y be the depth in kilometers of the quake below the surface at the epicenter. And they got this data. So put that in the calculator, make a scatter plot. And again, probably all you'll have to do after you put the data in is zoom stat. And I get that, which does not look linear at all. You might call that a weak positive, but more or less that doesn't look linear at all. Do my linreg to get my R, and I get an R of 0.511. Compare that to the table. I had 7 data values this time. So if I look at n equals 7 and alpha equals 0.05, I get 0.754 as my value on table A6. So compare what I got in the calculator to that, and 0.511 is less than what's on the table. So I can conclude that this correlation is not linear. So it didn't look linear, it's not linear. So how am I going to make a prediction? Well, you may remember from the very beginning of all this, to make a prediction when it's not linear, you have to use Y bar. You can find Y bar by doing 1 var stats of L2, because your Y values are in L2. Now I know that it says X bar here, but it was my Y values, so that's Y bar. So the best prediction for depth of any magnitude of earthquake per this data is 7.6 kilometers. I can still make a linear equation. It gave me A and B. It's just that linear equation is useless because this data is not linear. So I might on the test tell you to make the equation, but don't use it if the data is not linear. If the data is not linear, you have to do the average of the Y values. Okay, that's it. Told you chapter 10 was short. So fill out those notes and make sure and put them in Shobi or show them to me in class.